Hello everyone, welcome to COMP125 Principles of Computing. In this video we are going to continue our discussion about algorithm efficiency and analyzing the efficiency of the algorithm. Last week we have talked about important attributes for algorithms. Correctness of the algorithm is important, so that if you write an algorithm, you want the algorithm to be correct, to give you the correct answer. You want the algorithm to be clear and easy to read, and it has been written in an elegant way. And we want it to be efficient in terms of the amount of resources that they are using. It means it should be actually efficient in terms of space and time. So the focus of this chapter is on analyzing the efficiency of the algorithm, which basically answering this question that how carefully does the algorithm use the resources of the machine. So what are the resources? The resources are going to be the space, the memory that the algorithm is going to require to be executed, and how much time it would take for the algorithm to be executed. So this question that how much time the algorithm would need to be executed will depend on the machine. When you wanted to know that, for example, how long this algorithm is going to take, it definitely depends on the machine that you are running on it. Is the machine slow or very fast? But we don't care about the actual time. We care when we are actually doing the analysis of algorithms. We wanted to probably just compare different algorithms that does the same job, and we wanted to understand that which one is going to work better. So running the algorithms on some machine is not a good idea. The more, a better and a smarter approach is that we analyze the algorithms in terms of the amount of work that they need to be executed, to just actually give you the answer. And based on that amount of work, give an analysis of the efficiency of the algorithms. We have seen a couple of examples last week. I'm actually just repeating one of them, sequential search. The whole idea of the sequential search is that you have a specific target value. You are looking for it in a list of items. This algorithm that I copied it here, it is just actually copying from the chapter 2. In fact, the main problem statement was that you have a list of phone numbers, and you are going to look for a specific phone number in this list and find the corresponding name, associated name with that. Okay, so because the numbers hasn't been sorted, you have to look for check all of the numbers in your list. So you have a list of n phone numbers, and you have a target value that you are looking for. So that's going to be called number. You are looking for this in a list of n phone numbers. So this algorithm was actually creating a variable which actually is like a flag. We call it found. It has been initialized to no. And the whole idea of we have done the analysis. I'm going to just repeat it because we are going to get to more examples today. We have a loop here in our sequential search, and the main unit of work that will be repeated in this algorithm is going to be this line 4, which is comparing the number with each item in the list of phone numbers that we have. Okay, so this is something that will be repeated again and again and again until you find the number. And when you find it, actually, this line will stop you. Okay, so we did analyze the different scenarios that what would happen if the number that we are looking for is going to be T1. What would happen if the number that we are looking for is not in the list? And what would happen if the number that we are looking for is one of the numbers in the list on average? So it actually caused 3 different scenarios: the best, the worst case, the best case, and the average case. So the best case for any algorithm, remember, it was the scenario that caused the least amount of work that the algorithm needs to do. So in this case, the best case is going to be when the number is going to be t1. So if the number is t1, the loop will iterate only once, right? And then this if statement is going to be true, so number is equal to t1, right? So the value of found will be changed to yes, and then actually because of that, the while statement will stop, right? Because the while statement is not going to be, so the variable found is not going to be equal to yes, and the while statement will stop, and you actually get out of the loop. So the number of comparisons which is going to be required if the first number in the list is equal to the number we are looking for is going to be just one comparison, right? This is going to be the best case, the best scenario for us. So it actually just shows you that the number of comparisons is going to be one. So what is the worst case? The worst case scenario for us is going to be when the number is not in the list or the number is the last item in the list. In both cases, it's going to be actually the same. So in that case, you can see that this if statement will be executed n times, right? Because the number is not going to be equal to t1, t2, t3. So you have to compare it to all of these numbers until you reach to tn. And either if it is equal to tn or it is not in the list, you have to execute this comparison n times. So the number of times that you execute the comparison, or basically the number of times that this loop will be executed, is going to be equal to n. So that's going to give me the worst case scenario. Okay, so if the list is too long, the worst case, the number of actually comparison is going to grow. If n is a small, it will be a small. So it just actually tells me that it's going to depend on n linearly. And how about the average case? The average case is going to be, so if the number, you randomly actually choose a number and just compare it with the numbers in the list, what's going to be the average number of comparisons? So if you get the average over, randomly actually just get the average, it's going to be n divided by 2 number of comparisons will be required. So it's just like, on average, the number that you are looking for is going to be, for example, at the middle of the list, right? You can think of it in this way, that the number that you are looking for on average can be actually at the middle of the list. So if it is at the middle of the list, you are going to check n divided by 2 number of comparisons. Okay, so this is going to be the average case for us, which is going to be n divided by 2. Then we actually introduce the order of magnitude that we magnitude n that we actually showed it with theta n, which basically means that if the the amount of work that you need to do is going to be depending on n linearly, which means that the amount of work that you need to do is going to be some coefficient multiplied by n, which that coefficient is a fixed number. For example, it is half, it is 1, it is 2, it is 10. It doesn't matter what is that number. As far as that's going to be a constant number, we call it a C, and so then amount of work is going to be shown as Cn. Okay, so in that case, we say that our algorithm would actually need an order of magnitude of n to be executed, and we show it as theta of n. We also actually see another example. Remember the selection sort that we showed that the time complexity, the amount of work that we need to execute that was depending on n square. And we also actually draw some diagrams to show the difference between the growth ratio of those functions that depend on n linearly and those functions that depend on, n square. Okay, and the difference between them. So you can see that if an algorithm, the amount of work that the algorithm needs to do would depend on n square, so the algorithm is going to be slower because it needs to do more amount of work over the same size of the data. So by looking actually this figure actually just shows you that, for example, for 1, both of these two diagrams is going to give you the same. For 2, if your algorithm is going to depend on n, you would need 2, for example, unit of work. Although if your algorithm is going to depend on n square, it's going to take 4 unit of work. So it's clear that if your algorithm depends on n square, it's going to be slower because it needs to do more work. And then we also actually discussed about the, the effect of that constant that you are multiplying. So if your algorithm is Cn, is going to be actually definitely better and faster than if your algorithm is, for example, Cn power 2. And it doesn't matter what is the value of C. As far as C is a constant, we know that these type of algorithms that we show them as theta of n power 2 are going to be slower. This table here shows, compare, for example, n power 2 with a very small constant, compare it with n with a very large, relatively large constant. And it actually just shows you that when the size of the problem is actually growing, anyway, at some point, this term, a function like this, is going to be larger, which means that it's your algorithm. If your algorithm is going to take this amount of work, this is going to be slower, because you can see that, for example, when n reaches to 10 million, anyway, this is going to be bigger than when your algorithm is going to depend on n. Mainly the reason is that n power 2 is going to grow when the value of n grows, and this is going to grow faster than this coefficient. This coefficient is a fixed value, so at the end it's going to stop at some point, and n power 2 became anyway greater than n. It doesn't matter how small or how large is the constant value. Okay, so that was actually a recap from last week. This week I'm going to discuss 3 more problems, and for some of them actually more than one algorithm. So for this data cleanup problem, we will see 3 different algorithms and compare these algorithms that all of them are solving the same problem. All of them are solving the data cleanup problem, but we are going to actually just compare them and see that which one is going to work the best in terms of both the time and the space. Okay, so what is the problem? The data cleanup problem is that you have a collection of data, a set of actually, for example, numbers, that some of them are zeros, and we are not interested in zeros. We wanted to clean the data so that we remove all of those zeros and just keep all those data which are meaningful for us, and which means that they are not equal to 0, they are greater than 0. Okay, so this is the data cleanup problem. So for example, assume you have a list of numbers, like something like, for example, 1, 0, 3, 10, 0. At the end, you would like to get the list of all numbers which are not equal to 0. So you wanted to actually get 1, 3, and 10. Okay, so the data has been cleaned and you removed all of the zeros. So this is the problem statement. We are going to see 3 different algorithms. The first algorithm is called shuffle left algorithm, or I believe we also actually just call it shift left as well in some other texts. So what is the idea of the algorithm? The idea here is that we started from left to right and search for zeros. And whenever we see a zero, we try to shift all the items to the left. Okay, so let me actually just apply that algorithm over this example. So the idea is that you started from the beginning of the list and you go from left to right and check each item. So we check the first item, it is not equal to 0, that's okay. You go forward and check the next item, you go to the right, so check the next item. So this one I'm going to clean it. So the next item is 0. So what I'm going to do is that I will shift all of the other items to their left one. So it means that 32 will be actually will be shift to the left, 19 will be shift to the left, 0 will be shift, and 27 will be shift. So the result is going to look like this. So you can see that 32 has been shifted, 19, 0, and 27. So now you can see that this 27 is the previous copy. So that's okay, because what we are going to do is that we will define another variable that we call it legit, and that variable tells me that, okay, so I have checked until here, and there is going to be another variable. Let me show it with a different color. That variable called legit, and basically legit tells you that, okay, a different color. Legit tells me that previously legit was shown here, now legit will be updated to here, so that it tells me that, okay, until this part of the data is valid. So I know that this copy is not going to be valid. Later on I can just remove it. So don't worry about that copy. So again, what would happen is you actually go forward and check you go forward, you were actually here, you check the value, it is not equal to 0, so that's okay. You go to the right, you check the next item. So here you check the value, it is not equal to 0, okay, so that's fine. You go to the right. So the next item that you are checking is going to be this one, and that is going to be equal to 0. Then what would happen is you just shift all of the items after this point until you reach to the legit. You copy all of them to the left. So what would happen is this one is going to be copied here. So you can see that the result is going to be shown here. And then legit will be updated to refer to, let me actually use a different color. Legit will be updated to refer to here. So we know that, okay, from the beginning of the list until here will be valid, and then you will actually stop because you have checked all the items. So this is the idea. You started from left, you check each item. Whenever you see a 0, you shift all the items one to the left. So it's just like you will remove that 0. So this is the full algorithm written here. So as you can see, I have 3 variables. I have one variable called legit, which basically tells me that how many number of items in this list are valid items, okay? And I have a pointer which is called left. It started from the left and check each item. I have another pointer which is called right. So let me actually just run this algorithm, because we wanted to analyze this algorithm, right? So remember those two cases, the best case and the worst case. We wanted to check the best case, what would happen in the best case, how much work your algorithm would require to do in the best scenario, which means that the smallest amount of work that your algorithm would need to do, and what is going to be the worst case. So the thing is, in this algorithm, I am going to claim that the best case is going to happen when there is no zeros in your input. And then I'm going to actually just show you that why this is going to be the best case. So before that, one thing to keep in mind is that when we are analyzing the best case and the worst case scenario, what we are looking for is that we wanted to know how much work we are doing, okay? So what is, again, the central unit of work that we should care about? Just like in the sequential search, remember in the sequential search, we mentioned that this if statement here, this comparison was the unit of work. And at the end, we just actually analyzed that how many comparisons we would need in the best case and in the worst case. So I also need to actually mention that what is going to be the central unit of work that we are doing. So now you can actually see that I have a couple of variables, a variable left, which is going to be a pointer that is moving forward, right? I have a comparison that's basically is one of the main unit of work that I need, because it's just like for each item you are comparing it to 0 and check that if it is equal to 0 or not. So the number of comparisons here is one thing that I would care about. And there is one more thing which is important. You can see that there is another loop here which is doing that shifting the items, moving the items to the left. Okay, so this is another thing that I should be careful about it, because this is another, this copy that you are moving the items, you are shifting the items. So the number of shifts that you are doing here is going to be important as well. And you should be careful that the number of shifts here is going to depend on this loop and basically depend on the value of left and the value of right, both of these two variables. So let me actually just show you that what would happen if I have a list of items that all of the items are non-zero. So for example, if I have a list of items, let me write it using a different color. If I have a list of items like this, that 2, 3, 1, 5, 4. Let's actually just make it 3. It doesn't matter. So the number of items that I have here is going to be 6. N is going to be equal to 6. And let me actually just show you that what would happen in this case. We don't have any zeros. So the variable left, the variable legit will be actually just set to n, right? The variable left is going to be set to 1. So this is going to be left. This is going to be right. Okay, so left is 1, right is 2. So basically there are going to be some pointers over this list of items. So let me just actually simulate that what the algorithm does. It tells me that this while loop is iterating until the value of left is less than or equal to the value of legit. So let me actually just write all those values here as well. L, legit, and R. Okay, L is 1, legit is 6, and R is 2. Then it actually will do actually this comparison, right? If the item at position left is not equal to 0, then we have to actually do this set of statements. You can see that this loop tells me that if I don't see a value of 0 in my list, I would never go to the else part and never will actually do any shifting. This is why I'm saying this is going to be the best case. Because, of course, if you are shifting the items, it means that you are doing more work. And if you don't shift the items, it is going to be less amount of work. So when you don't have any zeros, I'm going to actually anyway run the algorithm in this over this example so that you would get a better understanding over it. But the important thing here is that when you are not having any zero in your input, what would happen is that the only thing that will be executed is increasing the value of left, increasing the value of right, and doing this comparison. So how much work you are doing? You are doing one comparison, one increment, and one increment here. So it's just like you are doing 3 work. How many times you are doing it? In actually equal to the number of items, because the value of legit is not changing. The value of legit is going to be equal to n. You initialized it as n at the beginning, right? And you are increasing the value of left by 1. So it's just like you started from 1 and you go to 2, 3, 4 until n. So how many times you are increasing and how many times you are actually executing these lines? N times. So n will be multiplied to 3. So this is the total amount of work that you are doing, right? The number of comparisons and the number of actually increasing over these variables, these pointers. So that's why I have actually written here that in the best case is going to be when there is no zero in the input, and the time complexity is going to be, the amount of work is going to be depend on n linearly. We just show that that's going to be just linear amount of work, linear amount of comparisons, and you are not doing any shifting. That's why it is going to be theta of n. So what would happen if you have some zeros in your list? You can see that based on if you read the algorithm, let me actually just clean up here. If you read the algorithm, you will see that you have this loop here, okay, that will, basically iterate n times. And in your loop, you have this if statement. Whenever the if statement became false, which means that whenever you find a zero, you will go to the else part, right? So this part of the code, this part of your algorithm will be executed only when you find a zero. When you find a zero, okay? So you will shifting the items whenever you see a zero. And shifting is going to be costly, because when you are shifting the items, for example, let me show you one example that you have a zero. For example, when you have a zero here, what would happen in that case? So, or at the beginning of the list, let me actually just make it at the beginning of the list so that it is even more clear that what would happen. Okay, so in that case, let me use a different color here. The value of L is 1, the value of right is 2. Okay, you check the value of item at position left, it is equal to 0, so you go to the else part. Then what you are doing is that you will reduce the value of legit, so the value of legit will be 5, and then you are running this loop. This loop basically tells you that variable r was for shifting. It tells you that this loop here is going to shift all the items from position r to the end. So what it actually does is that it copies the item at position right into position right -1. So it's just like you are going to actually copy this item here. So although it is actually 0, it doesn't really matter. I'm going to, or even actually to make it more clear if you are not really getting the idea. let me use a different color here. For example, 3. So what would happen here is that the value at the position R will be copied at the position R minus 1. So 1 copy, 2 copies, 3 copies, 4 copies, and 5 copies. Basically, what would happen is that if the first item, be careful, when the first item is 0, how many copies, how many shifts I am doing here? N minus 1 shifts, right? Because except the first item, all the numbers at the position 2 to n will be shifted to the left. So n minus 1 shifts will be required when the first item is 0. So let me actually just write it down here. First item. So let me actually just mark down them as let's create a list of a table of items that tells you that, okay, find 0 at index 1, 2, 3, and we actually go until we reach to index n. Number of shifts. Or copies. Okay, the number of shifts or copies. If the first item is 1, the number of shifts is, if the first item is 0, the number of shifts is going to be n minus 1, right? If the second item is also 0, the number of shifts this time is going to be n minus 2. Let me actually just show you that what would happen if the second item is also 0. Okay, so far, what happened, the value of left was 1 from before. The value of legit has been decreased by 1, so it became actually 5. You can think of it as n minus 1. And then the value of R, what is going to be happening to the value of R? Okay, the value of R after you are done with the shifts are going to be set to left plus 1. So the value of R will be actually reset to 2 as well after you are done with the first shift. Okay, so this is the thing. So it's just like the value of left and right hasn't been changed. Still they are referring to this item and this item. So the second item is also 0, right? So what would happen in this case? It's just like when you are done with the shifting, it should be look like this. So 1 will be actually copied here, 5, 4, and 3. Okay, so it is the result of the, the result of the list after you are done with shifting the first item. So the first item is gone. Now you can see that even the second item is also 0. So the original list was something like this. This is the original list. 1, 5, 4, and 3. This is the original list. And now after one iteration of this loop and shifting all the items once here, we actually get to this result. Now again, what would happen? You compare the value at the position left. You can see that this is again 0. It is again 0. You come here. And what you are doing, you will shifting all the items to the right. You can see that the legit will be decreased by 1. So legit will be 4. And then you will shifting all the items to the right. How? Using this a pointer right. So what's going to happen is that this item will be copied. Let me use a different color. This item will be copied here. Then R will be updated to this. Okay, then this one will be actually copied again. Then R will be updated here. Then this one will be actually again updated. Then R will be set to here. So this one will be copied as well. So I forgot to actually to do the updates as well. So this one will be 1. This one will be 5. This one will be 4. And this one will be 3. Okay, so it will actually, how many shifts for the second 0 happened? The number of shifts was, in this case, it was actually 4 shifts, or n-2 number of shifts. So what would happen, how many times you are shifting if the third item is also 0? If the third item is also 0, the number of shifts is going to be n-3. So it's just like, you know, as you are going down, the number of shifts are also decreasing. But at the end, you have to add up all of these number of shifts. So you have to add n-1 shifts plus n-2 shifts plus n-3 shifts plus, until you actually reach to 0 number of shifts for n. Okay, so what is this summation? We got exactly similar formula when we discussed about the selection sort, right? So this summation is going to be equal to n-1 divided by 2. So it's going to be n power 2 divided by 2 plus, minus n divided by 2. So at the end, what you are actually seeing is that, yes, I am going to have a term which is n square. So this time complexity, I mean the time that your algorithm is going to need to be executed in the worst case is going to be theta of n power 2. And the worst case scenario for this data cleanup algorithm is going to be when all of the items are 0 and you need to basically shift all of the items each time that you are iterating in your algorithm. The first time the number of shifts are going to be n-1, the second time n-2, n-3, until you reach to 1. So this is going to be the worst case scenario. And basically, I can actually just say that if you have, on the average case, if half of the items are going to be 0, the average case that I don't have it here, but the average case is going to be when half of the items are 0, and so you are going to shift for half of the items. So on average, again, you are going to need n power 2, n power 2 multiplied by something, some constant. But anyway, it is going to be in order of n squared. So even in the average case, your algorithm is going to work in n power 2. How much space your algorithm would need? You can see that based on this algorithm that we see, we just need a couple of variables, legit, left, right, okay, except the data, the list of data that you get. Except this, you are going to only use a couple of local variables. So a handful number of local variables. So the amount of space that you are required is going to be, a fixed amount of work. So if you are working on a list of n, except the input list, you are not using, more space than that. You just have, just a couple of variables, nothing more than that. Okay, the second algorithm that I would like to discuss here, again, this algorithm is going to be an algorithm for data cleanup problem, but the algorithm is called copy over. Okay, so the idea of the copy over is that we are going to use additional array. We are going to use additional list. So we are going to create an additional list, and initially that list will be empty. Okay, so we create a second list. Initially it is empty. Then we are looking at each item in your input list and checking it. If it is not equal to 0, we are interested in that. Okay, so we are copying it into the second list. So the whole idea here is that we are going to check all the items in the list, and whenever we see an interesting item which is not equal to 0, I'm going to copy it into this new list. So at the end, those interesting items that I would like to have them, I will have them in the second list. So the second list will be the answer. So let me run that example over this, that algorithm over this example. So at the beginning, you are going to have, let me actually show it in this way. You are going to have an empty list, right? And then you check the first item in your list. Is it equal to 0? No, it is not. So it is going to be an interesting item. So what I'm going to do is that I'm going to add it to this new list that I have. Then you will actually update your pointer and see the second item. The second item is going to be 0. Are you interested? No. So forget about that. I'm going to look at the next item in the list. So the next item again is going to be, so we can see that after, when I'm actually just checking this 0, I'm not changing the second list. So the second list remain as the previous. So it's going to be only 55. So whenever I'm checking the next item in the list, I found something interesting. 32 is not equal to 0, so I'm going to add it to my list. So this is going to be 55, and then 32 will be added to the list. Then I will check the next item in the original list. Is it equal to 0? No. So we will add it to our list, to the second list. 19. So then we are going to check the next item in the list. Is it equal to 0? Yes. So I'm not going to change this list. So it's just like, it is going to be just like before. Then you update the pointer. The next item is going to be not 0. So it is interesting. I'm going to add it to my list again. (19) and 27 will be actually copied. So at the end, the list that I have is going to be this one. I'm done with checking all of the items. This pointer reached to the end, and you would stop and return this array, this new list of items as the final answer. This is the algorithm that is actually in figure 15 of your chapter 3. So you can see that here we have an input. It's going to be a data list, n data list item, and we know that what is the value of n. We are going to have a variable left that initialized as 1. So this pointer or variable is going to change over the or input variable or input list. And this new position is actually just tell us that what is the end of the second list that we have created. Okay, when we are going to analyze this algorithm, again, we are going to be interested in the best case scenario and in the worst case scenario, right? So the first thing that we should figure out is going to be the central unit of work that we are doing. I am going to have a loop, right? This loop is going to iterate. Let's just see that which part is going to be, frequently just repeating. That's going to be the central unit of work. So you can see that I have a comparison here. Again, this comparison is just checking each item at the position left. So the first thing that we know that it's going to happening, repeatedly happening, is this comparison. And the second is that whenever you find a non-zero value, you can see that you will copy that variable into the new list. Okay, so this copying the item into the new list is also something that's happening. But the good thing about this one is that this is just one item of work, one simple instruction that you will do. This is not like a shifting. It's just like, okay, one thing will be added to this new list. So this is just one thing that you are doing, just like the comparison, that this is one work, one unit of work that you are doing. This is also one unit of work that you will do. And you have one unit of work here that's actually just increasing the value here, and you have one unit of work here that you increase the pointer as well. Okay, so let's just see that what's going to be the best case scenario, what's going to be the worst case scenario. So the number of comparisons here, this if statement will always be executed, right? So it doesn't matter if all of your item in your list is 0 or all of your items in the list are non-zero, you will compare them to 0, right? You will compare all the items in your list. Let me actually just draw 2 examples showing that, for example, all of the items are 0, all of the items are non-zero. The first, all of the items are non-zero. So let's actually just check that all of the items are 0. So something like this, 0, 0, 0, 0. And so this is going to be our input list. This is going to be the new list that we create. Okay. When all of your actual items are 0, this is going to be left. Okay, the pointer left that initialize that as 1, and this is going to be that new position. New position, I'm just showing it as new P. That's also referring to 1. Okay, you will compare the first item with 0. It is 0. Then because it is 0, you are not going to execute inside the loop. So what you are doing is just increasing the value of left. So left now is going to refer to this. Okay, so this comparison has been done, but this part hasn't been done here. So if the next item is also 0, again, this comparison will be done, but this part, the body of the if statement will not be, you are not actually copying the items, right? So when all the items, just think about it in this way, whenever all the items are 0s, you are not copying anything to the new list. Okay, but you will compare them with, you will compare all of the items anyway, and you are increasing the value of left as well. So it's just like you are doing two unit of work, how many times? Equal to the number of items in your list. So the amount of work that you are doing is going to be 2 multiplied by n, just think about it in this way, and then so it's going to be cn, so it's going to be theta of n. This is going to be the best time complex, the best scenario, the best case. What is going to be the worst case? The worst case is going to be when all the items that you have are going to be non-zero. So in that case, let's just assume that all of these items are non-zero. Okay, so again, you have left here, you compare the first item with 0, it is not equal to 0. So what you are going to do is this part will be executed. So you copy the item into the new list and you increase the value of new position. So what would happen is that you copy the item, so 3 will be updated, and new position will be actually just updated as well to 2. Okay, then the value of L will be updated, so it's just like you are checking the next item in your list. again, the next item in your list is not 0. Okay, so you copy it in your new list. So 5 will also be copied. And for the rest of the items, so 6 will also be copied, 2 will be also copied, and then 1 will also be copied. Okay, so in this case, you can see that this comparison will be executed, this copy will be executed, and this increase will be executed, and this one will also be executed. So how many unit of work? It's just like you are doing 4 unit of work. How many times? N times. So even for the worst case, although the constant has been changed, this is going to be 4n, but even for the worst case, this is going to take theta of n. It is going to depend on n. This algorithm is going to be more efficient than the previous algorithm. Remember, in the previous algorithm, the worst case was n power 2 because of those shifts that we have. But here we are not having shifting. Instead of shifting, we created a new list and copied the items to this new list. Okay, so what's going on here, the best case and the worst case, both of them are going to be, linear. They are going to depend on n linearly. They are going to be theta of n. So the average case is going to be the same as the best case and the worst case as well. But although this algorithm is going to be more efficient in terms of time than the previous algorithm, but one thing that you should be worried and you should know that the amount of space that we are using in this algorithm is different than the previous algorithm. In that shuffle left algorithm, we didn't use additional memory. But here you are creating a new list and you are copying all the items. Specifically, when you are having the worst case, which means that you don't have any 0, you will copy all the items from the previous list to this new list. Okay, so you are using a full list. In this case, actually, for the space complexity of this algorithm, we are going to have a best case and worst case analysis. So the best case is going to be when all of the items are 0, so you are not going to use any additional space. If all of the items are 0, you are not going to copy them in the new list, right? So in that case, you are not using more space. But if all of the items are non-zero, you are going to use additional space, additional n amount of space, right? Because you are going to copy all of those n non-zero items. So you can see that this algorithm, there's a trade-off between this algorithm and the other algorithm. This algorithm is going to use less amount of time, but it's going to use more amount of space than the previous algorithm. Okay, so far we saw 2 algorithms for the data cleanup. One of them are doing better in terms of time. The other one is doing better in terms of space. So now I'm going to show you another algorithm for the same problem, data cleanup, which basically solves both of those issues. This algorithm is going to be both efficient in terms of time and space. This is going to be very interesting. We call this algorithm converging pointers. Okay, so the idea of this algorithm is we keep 2 pointers and one left pointer that again started from left and check all the items from left, and it actually moves forward, and another pointer that started from the right. This is going to be called the right pointer, and this pointer is not moving until we find a 0 from the left. Whenever you find a 0 from the left, what would happen is that you copy the item at the pointer right into the position of the 0, and then you actually shift the pointer right to the left by 1. Okay, and then you stop whenever the left pointer is passing the right pointer, or they actually just reach to each other. So this is going to be the algorithm, and don't worry, I'm going to run it over an example so it would be more clear that what's happening here. So again, the input is going to be n and a list of n items. We are going to actually have a variable legit. That again, this variable, the responsibility of this variable is to just tell you that how many items in the list are going to be. At the end, it will tells us that until which part of the item are going to be the valid items in the list, because all of those non-valid items will be at the end of the array. It's exactly like the responsibility of legit in the other algorithms. I have 2 pointers left that actually initialize at 1 and right, which is initialized at n. Let me actually just show that how this algorithm works over an example. Let me just show it to you over this example. Like, for example, 3, 0, 4, 0, 5, 1, 6. Let's actually just make something interesting. So I am going to, maybe that would be better to use a different, a black color here. 3, 0, 4, 0, 5, 1, and 6. So left is going to start it from here, and the right is going to be started at n. Okay, so this while loop is going to actually iterate in this way. You check actually each item at the position left. You check each item at the pointer left. And if it is not equal to 0, you just actually move forward, because if it is not equal to 0, we are okay. We want that item. So just move forward and check the next item. Okay, so if the item is not equal to 0, just increase it. But if it is equal to 0, we are doing something different. But let's just actually just go forward here and see that what's happening. When L is equal to 1, the item at position 1 is not 0, so L will be updated. So in the next step, the best thing here is that, let me just clean up a little bit here. So I'm going to just repeat that array 4, 0, 5, 1, and 6. So still R is here, but L is now here, okay? So in the next step, again, you compare the value of at position left with 0. Is it equal to 0? Yes, it is equal to 0. Then this part needs to be executed. It actually reduced the value of legit. Let's actually just write legit here. Legit was 7 previously. Here we actually decrease it and make it 6. And then what we are doing is that you copy the item at position right into the item at the position left. So what will be happening is that 6 will be copied here. So it's just like I'm showing you the new position, new status of the list in this way. So 6 will be copied here. And then the value of right will be reduced. So R will be here, and you can see that we didn't change L. L didn't actually increase. Okay, so again, you actually go back to the while, because left is still, L is still, left is still smaller than right. You continue. You compare the value at the position left with 0. Is it equal to 0? No. Okay, So 6 is not equal to 0. You increase the value of L. So you increase the value of L. It's just like, let me just show it to you in this way. I just try to show you all the process step by step. So you increase the value of L. So L will refer to the 4 this time, and R hasn't been changed. Okay, so R is just like before. In the next step, again, your loop will actually continue repeating because left is still smaller than right. Okay, so you check the value at item left, compare it to 0. Is it equal to 0? No, it's not equal to 0. So what you are doing is just you are increasing the value of left. Because I don't have a space, let me just update it here. The value of left will be updated here. Okay, so again you continue doing the loop because L is still smaller than R. You compare the item at position left with 0. Is it equal to 0? Yes. So because it is equal, you are going to execute the else part. The else part will update the legit, and it will copy the item at position R to the item at position L. So the new status of the list will be like this. Because I didn't have a space, I'm writing it here. 3, 6, 4, 1 will be actually copied in this place. 5, 1, 6. And then you just reduce the amount of the actually the pointer right. So the pointer right is going to refer to this. This is going to be pointer left, because you are not actually updating left, right? And this is the result after the end of actually this line. So again, still left is smaller than right. So you compare the item at the position left with 0. Is it equal to 0? No, it is not equal to 0. So what you are doing is just increasing the left. So left will be increased. And so left and right, both of them are referring to the same position. It's just like both of them are referring to this position in the list. Okay, so you are going to back to checking the condition of the loop. Condition of the loop, it tells you that while left is less than right, you continue. But your left pointer has reached to right. So your algorithm will stop. Your algorithm will stop, but the thing is, still this item hasn't been examined. This item needs to be examined. This item can be 0. What's going to happen here is that we are checking the value at position left here. This is going to be the last item that will be checked. If it is equal to 0, we reduce the value of legit. So just assume that if it was 0, legit will be 4, which actually tells me that this part of the array is going to be the valid part. But in this example, the item at the position L is not 0. So what's going to happen? Legit will be still 5, which tells me that at the end, when I stop here, 5 items from the beginning of the list, 5 items are going to be the valid items. And so this is going to be all the non-zero items. Okay, you can see that all the non-zero items, which was 3, 4, 5, 1, and 6, are in this part of the array, which are actually copied, and we actually preserved all of them. Okay, so now analyzing the algorithm. The central unit of work that we are doing here is, again, comparison, right? You can see that we actually have this comparison in all of these algorithms. So this comparing the item at position left with 0, this is something that we will execute. Not only that, we are, I can actually just see that we don't have any shifting here. We didn't actually create a new array, right? We just actually did all of the work over the original array. I didn't use additional array. I didn't use additional list of items. Unlike actually the previous algorithm that I created a new list and copied all the non-zero items to that new list, I didn't do that. But yet I'm doing something here. I am updating the 2 pointers. I'm updating the left pointer, and I'm updating the right pointer, and I'm actually copying the items at the right. Whenever I find a 0, I will copy the item at the position right to the item at the position left. Okay, so this copy and this update of the right and the update of the left, these are some things that I would repeatedly doing. But now let's see that how many times I'm doing this. This comparison will always be applied, right? So if I have n items, the comparison here will always be, so let me actually just write them here. Comparing item at position left with 0. So this is always will be doing. So n number of comparison I will do. How many times I will increase left? It will depend on the number of zeros in the list, right? So if I don't have any zeros, the number of, so increasing pointer left, increasing left, how many times I'm actually executing this? It depends on the number of zeros. If I don't have any number of 0, this is going to be executed n times. If all the items are zeros, this is going to be 0. So this is going to be equal to the number of non-zero items. Okay, this is important. What are the other actually actions that you will do? This is the one of the things you are copying the item at position R to the item at position left. Okay, and you are reducing the right. So reducing right, reducing R and copy. How many times this one will be executed? You can see that this is a part of the else. So whenever I see a 0, this will be executed. So the number of times that I will copy an item and I will reduce the value of R is going to be equal to the number of zeros in the list. So this is going to be equal to the number of 0 items. Okay, so the nice thing is that in total, I wanted to know that how many times all of these will be executed. So if I actually just add up all of them, this comparison is going to happen n times. The number of increment of left and the number of actually reducing of R and copying are going to be complement of each other. If I have, for example, n items and k number of them are 0, I would have n minus k. So let me actually just write it in this way. These are complements, so that if the number of 0 items, if the number of 0 items is k, the number of non-zero items is going to be n minus k, right? So in total, the summation of number of times that you reduce and copy and the number of times that you increase the left pointer is going to be equal to n. You know, the summation of them is going to be equal to n. So there is basically the worst case and the best case for this algorithm, both of them are the same. When all of the items are 0, so basically you always going to actually just copy an item from the right and you just decrease the value of r. If all of the items are non-zero, always just the left pointer is going to increase. So in both cases, the amount of work that you are doing is the same. It is going to be depending on n. And this algorithm is going to do in theta of n in the worst case and in the best case. Basically, actually, the worst case and the best case are going to be the same. And the nice thing about this algorithm is that we are not using additional space as well. The amount of space that we used was just, a handful number of variables in addition to the input list that we have. We didn't use an additional list, unlike the second algorithm. So here is, the summary of all the algorithms that we have discussed for the data cleanup. Shuffle left, copy over, and converging pointer. You can see that I have actually written all the best case, average case, and the worst case and the average case for all of these algorithms. We saw that for the shuffle left, the best time complexity is linear when all the items are non-zero, and the worst case is going to be n power 2, and the average case is also going to be n power 2 n squared. So this is going to be the worst algorithm in terms of time. But the amount of space that was used for shuffle left was just the input list. So if you are storing your input list in, your size of list is n, this is the only main space that you are using. The copy over would use additional array. That's why the amount of space that we are actually going to use is going to increase, because we are going to use additional array of the same size, additional list of the same size. But the good thing about this one is that all of the time complexity in the best case and the worst case are going to be linear. And then we saw a better algorithm that both in terms of the space and the time, it is more efficient than the previous algorithm. The time complexity is going to be linear, and the space complexity is also, and it's not going to use additional space, in addition to the input list that it gets. So obviously, so you can see that although I just reviewed 3 different algorithms for the same problem, and now you can see that by having this tool that you analyze the efficiency of the algorithms in terms of space and time, it's going to be much easier for you to choose. So the algorithm analysis is actually a tool that helps you to find the best algorithm that solve a problem, because in many cases you have a problem and you can actually come up with different algorithms. So analyzing the algorithms helps you to find the best algorithm. You can actually just analyze it in terms of both time and space and choose the best algorithm based on the output of the analysis.